people. Hey, look, Doc, I'm going to cut that off. You are good people. I'll leave that as a start. Okay, let's get started. So we're going to talk about radiometric dating. We already asked and people answered. This is the Shroud of Turin. So to start with radiometric dating, a simple question. This is not radiometric dating. This is nuclear power. Why must neutrons be thermal to produce a nuclear fission chain reaction? You've already answered it once. They're only likely to absorb slow neutrons. That's right. And so we have to slow them down. That's why we have moderators in our nuclear reactors to slow them down. But then, of course, if you moderate them all, you're going to have a bomb. So in our nuclear reactors, we also have the control rods to absorb neutrons so we don't have a bomb. In a bomb, well, we don't care. We want them to slow down. We want them to be absorbed. If you have enough mass, you can make that happen. Two simple designs for a nuclear fission bomb is you have, here is mass 1, here is mass 2. Just for fun, let's put some kind of lead barriers between them. Each one of those might be about, let's say, 4/5 the critical mass. That means it's not enough mass for you to have at least one neutron from each fission going on to cause another one. But then you remove those two pieces of lead, which I just put in there randomly for the fun of it to shield them, and you make them go together. So basically you put a little explosive, you keep one fixed, you put a little explosive back here, it goes boom, and it makes this come over here. And then you have mass 1 and mass 2, 4/5 plus 4/5 is 8/5 the critical mass. You have more mass than the minimum amount for them to, on average, slow down and have another reaction, and then it goes kablooey. Simple, right?
Yeah, as long as you're not too close.
Yeah, you don't want to ever be too close to a nuclear bomb. Another device is a sphere that has a whole bunch of little pieces. And then for detonation, what do? You make them all go toward the center. And you make a critical mass that way. That actually allows you to have a better geometry to get a bigger yield. So those are fission bomb designs. What about a fusion bomb? How do you suppose they make a fusion bomb? What do you need to make hydrogen fuse into helium? Okay, a lot of energy, which means a high temperature. You need high temperature and pressure. A lot of pressure to make it so there's a high probability of them colliding. So you have those two things. And how do you make that happen? With a fission bomb. So to make a fusion bomb, you start with the fission bomb to get the conditions necessary for the fusion bomb. So you have a pre-bomb, a little fission bomb, and then you have the real bomb, the fusion bomb. And that's all we're going to talk about bombs.
Yeah, I think you said that one too many times. You may be on a watch list.
I am not. Okay, moving forward with the topics, we are going to talk about radiometric dating before we start reviewing. So a question just to make sure you remember from lab, approximately how many half-lives result in less than 0.1% of the original nuclei remaining? So that's 1/1000th remaining.
It'd be pretty quick, I would think.
Well, how many half-lives? 1, 2, 3, 4, 5. How much is left after one half-life? Half. How much is left after two half-lives? Quarter. How much after 3? Okay, so how many people are computer scientists here? Because computer scientists know all these numbers. How much is left after 4? 1/16. After 5? After 6?
162.
64. 128. All right, then. That's not it yet, is it? We need to go another factor of 10. So that was 7 after 8,
256.
after 9,
512.
after 10,
1,000 and whatever.
1,028, or 1,024.
So 10.
So it's going to have to go through roughly 10 half-lives to have 0.1% remaining. That's actually important. We're going to talk about carbon dating. Carbon has a half-life of 5,730 years. So 10 half-lives for carbon is approximately 57,000 years. Now, why is that 0.1% number important? Well, we start off with the fact that carbon-14 is a very small percentage of the carbon that we have. Most carbon is carbon-12. Carbon-14 is created in the atmosphere. You have, I cut out these things for my lecture, but you have a neutron hits a nitrogen that produces number on the bottom, 0 plus 7 is 7. Number on the top, 1 plus 14 is 15. Produces an unstable nitrogen 15. That nitrogen 15 then decays into carbon 14 plus, well, what am I going to have? I had 7 protons in the nucleus. Now I have 6. So what do I have to have?
Hydrogen. Oh, no.
Hydrogen actually would be a correct answer. We call it a proton here, but if I put hydrogen 1 with a plus, a hydrogen ion, that would also have been perfectly legit. So that's the process that is creating carbon-14 in the atmosphere. What makes it occur? It occurs because of these neutrons. Where are those neutrons coming from? From the sun. The sun is blasting us with protons, neutrons, neutrinos, all kinds of stuff. And so the sun, these neutrons are causing carbon-14 to be created in our atmosphere. But there's not much of it there. The carbon-14 decays. Carbon-14's decay is similar to that. It's carbon-14 decay. Actually, it has multiple decay routes, but now if you look at that, what's wrong? The number of protons went up, but the number of neutrons stayed the same. This is actually the relationship. A proton suddenly spontaneously, a neutron suddenly spontaneously was destroyed and replaced by a proton, an electron, and this electron antineutrino. And so you started with nitrogen 14, you absorbed a neutron, you kicked off a proton, you became carbon-14. And then that carbon-14 kicks an electron out of the nucleus and becomes a nitrogen-14. Now, if you look at the charge state, this nitrogen-14 has a plus charge because it still only has 6 electrons. And the beta particle, what's another name for a beta particle? Electron, yep. The electron has a negative charge, so your charge has been conserved. In particle physics, conservation laws are super important. And protons aren't conserved. Neutrons aren't conserved. Baryons are conserved. What's a baryon? Well, a proton's an example of a baryon. A neutron's an example of a baryon. So we have the baryons conserved, but not the protons and the neutrons. We have charge conserved. We have a few other things conserved, and some things that we say are partially conserved, and we aren't getting to that. So how does carbon-14 dating work then? They measure, this R is actually not representing the activity like it did in lab. That R is standing for ratio, the ratio of carbon-14 to carbon-12. So you find a sample that used to be living. It has to be something that used to be living, something that exchanged with the environment. We, as we live, we eat food. And that food had photosynthesis going on. That food brought in carbon from the atmosphere. And so the ratio of carbon-14 to carbon-12 in the food is reflective of the ratio of carbon-12 to 14 in the atmosphere. Then we eat that food, and the ratio of carbon-14 to carbon-12 in our bodies is reflective of the ratio in the atmosphere. Now, something I find really interesting. I used to be really big into watching the Tour de France. Wasn't that big of a bicycle race, just Tour de France. And then we had everybody, the revelations of their cheating. And the one that really turned me was it Levi Leipheimer? I don't know, one of the American cyclists. He, one day he just cracked and he lost 15 minutes. And the next day, he just stomped everyone and gained the lead back. It was wow, best comeback ever. Well, that day he tested positive for testosterone. And so everybody's I've never done it. I wouldn't cheat. How does the testing work? First of all, they're measuring Hey, Leslie. They're measuring how much testosterone or breakdown products of testosterone you have in your body. And if it's more than 5 times the standard amount, then they flag you as testing positive. But that's just a flag for testing positive. That doesn't mean that you actually are going to be considered a positive test, because they run a second test that's an isotopic abundance test. They're not measuring carbon-14, they're measuring carbon-13 to carbon-12 ratio. Carbon-13 is stable, carbon-12 is stable, but in different temperatures, the uptakes of carbon-13 to carbon-12 are slightly different. And so food that is grown in certain regions will have a different ratio than food in other regions. And our standard diet is based on food in this region with this ratio. But synthetic testosterone is making soybeans, which are grown in a different environment, have a different ratio. And so the definitive test of, is that your looking at the isotopic ratio of carbon-13 to carbon-12. And when that ratio is off, then there's really only 2 answers. Either, well, I get all my protein from all in the food, or synthetic testosterone. And so, that's what I learned from the Tour de France. Has something to do with this, because you're measuring the ratio of carbon-14 to carbon-12 that you have in this thing you found. So I find a bone, right? That's something that used to be living. And so I take the carbon there and I examine it, and I have to measure what that ratio is. The ins and outs of measuring that ratio, that's something we're not going to be worried about here. But because you already start with a small ratio, if you drop to 1,000th of that, it's essentially non-measurable. And so that's why I asked you the first question about how many half-lives roughly to get to 1.1%. That's as long as you can measure with carbon-14 dating. So you can only measure out to about 57,000 years with carbon-14 dating. If you are a young Earth creationist, that's highly significant. If you believe that the Earth has had life for millions of years, right, you ascribe to the standard scientific explanation that says that the Cambrian explosion occurred 541 roughly million years ago, and that you had the dinosaurs roaming the Earth roughly 70 million years ago. 50,000 years is meaningless. Now, I have to point out right now, I have always had great faith in radiometric dating. We had one of the people who actually came up with the idea of radiometric dating giving a talk at PHYS, and I asked a question that's a very legitimate question, I thought. And somebody said, well, another teacher said, you know why he asked that? Because he doesn't believe in radiometric dating. He was trying to undermine it, which was not true. I truly believed it. But now I am a little less believing it, because they have found dinosaurs that have measurable amounts of carbon-14 in them and that have soft tissue. And soft tissue shouldn't last for much more than 1,000 years. And you have something that's supposed to be millions of years old and it has soft tissues. And then you have carbon-14 that certainly shouldn't be there after more than 100,000 years at the very outside. You shouldn't be able to measure anything, and they're measuring some. It's very confusing, to say the least. And so I'm starting to have less confidence in it. But yet, I'm teaching it to you because it's science and we need to know what it is. So they simply take that sample and they measure the ratio now. And how does the ratio now help you to know how old it is?
You would extrapolate.
You extrapolate using this equation here. So you just say time is equal to the minus the natural log of the ratio now to the ratio it started with, divided by the decay constant. But here's the thing. How do we know what the ratio was when it started?
We make an assumption.
We make an assumption. Now, a lot of young Earth creationists get this wrong. You start with a very naive, we know incorrect assumption that the ratio that there used to be in the atmosphere is the ratio there is now. It makes sense, right? But it's not really true. So I listed some assumptions. The ratio is well calibrated is what we actually use. That's a naive assumption to say it was constant. And then we have the assumption that the half-life has remained constant. Assumption of the half-life remaining constant appears to be very valid to most of us. If the half-lives change, well, that throws everything off. That organisms maintain a C14 to C12 ratio identical to that in the atmosphere during their life. That's a pretty good assumption, we believe. And the organisms did not exchange carbon after death. Pretty solid assumption, right? They're not doing much respiration or eating. But here's some historical, we believe, atmospheric concentrations of carbon-14. Now, I don't even know if the units are here. What I care is you can see that there's variation in the ratios. And the variations actually are having to do with the temperature of the atmosphere. So when you have a minimum, like the Maunder minimum, Earth temperatures were much cooler then. And with the Earth temperatures much cooler, you had, once again, I don't even know how to read this, so I don't know if that's more or less. But you had a different amount of carbon-14. And when the temperatures are warmer, and so you can see here we are at our modern max, the amount of carbon-14 to carbon-12 in the atmosphere has been rising since the Maunder minimum. Being more specific, I always like this because I was born here. Just before I was born, something significant happened. The amount of carbon-14 in the atmosphere nearly doubled. Well, if you were making the assumption the carbon-14 level in the atmosphere is constant, your dates are going to be off by a factor of 2, right? That's a significant problem. Anybody have any idea what that was?
Revolution.
Atomic bomb detonated in the atmosphere. Shooting out a whole lot of neutrons, causing a whole lot of carbon-14 to be created. So clearly we can make some significant changes. Volcanic eruptions will make differences. So what is done is they carefully calibrate. You find something that you know its date. Maybe it's archaeological. So you have something that, from Sneferu, whoever that is, or the time of Zoser. You find this artifact. And you do radiometric dating, and from other things, from historical documents, you know when that thing was buried. And so then you date, how much do we have now? This is how old it is, and you can just use that same extrapolation to get what the ratio was when it was buried. And you assume, like a tree, well, it must have died somewhere close to there. And so that's how this calibration curve is actually made. And here is reality. You guys ever heard of Utsi? Utsi was a person who was found by hikers. When I say person, I think we say he's a Neanderthal. Is that right? I can't remember what they call him in terms of the term, Neanderthal, Homo this, Homo that. But they found this body buried in ice. And so this body was carefully taken out, and they're like, how old is this body? When was it frozen in the ice? And so they did carbon-14 dating on it. And doing the carbon-14 dating, they say, well, okay, we have this ratio that would give us this age. The upper one and the lower one, this is just a blow up of the little region in the upper one. So this upper one, you can see here is the uncalibrated line. This is what you would have for calibrating the age. So you would say with this, with the sample, you would say that it's approximately that old. But they're like, let's actually do it carefully. Let's not take these naive assumptions. And so this tree ring calibration curve is showing how much carbon-14 to carbon-12 ratio there is by examining trees and saying, okay, so this tree just died. This is a ring that was laid down this many rings ago. The assumption that one ring per year seems legit tells you that long ago, this is what the ratio was. Because the trees, each ring is laid down in a season, and they don't exchange after they're laid down. So they can calibrate this, and so they say, okay, now we have our measurement is at this level with uncertainty that could be as high as this or as low as this. And so let's look at where that crosses the calibration curve. And so you have a crossing here, and then you have it just tapping in there and tapping in here. And so the time that's shown below is the time range going from these dashed lines. So zooming in on that, then they determine that there is a certain likelihood that it's this age plus or minus about that, and a certain likelihood that it's this age plus or minus that, and a certain likelihood of this age plus or minus that. So they have 3 ages that they calculate for this sample. It depends on the sample, what you're going to get. And so I have over here the actual numbers. So they the values are 3,360. Okay, I have something written wrong there. You're right. It's not 3,360 plus or minus 3,330. I obviously wrote something wrong there because that uncertainty doesn't make sense. I think it's supposed to be between 3,330 and 3,360 is what I think it's supposed to be. For 68.2% confidence, or 3,210 to 3,190, or 3,160 to 3,130. So they have those 3 with certain percentages for what its age would be. And putting it all together, they get, I've got to go through and fix these numbers. That's ridiculous. But they get their final age by taking these 3 possible ages and combining to say the most likely age is this plus or minus this. So it's very carefully done. That's my point. They're taking those ratios. They're taking just the radioactive decay like you did in lab, but they've got to calibrate those ratios. Now, this only works for things that are relatively recent. What do you do for something that's old? Let's say you find a rock that you believe to be a rock that was created when the Earth was created. You can't date it with this technique. You'd have to date with something with a longer half-life. Now, I should point out, I said they're finding carbon-14 in these dinosaur bones. It wasn't until the last decade that anyone ever considered doing carbon-14 dating on them because they all knew it couldn't have any carbon-14. But when they found soft tissue in the dinosaurs, that's when somebody said, hey, maybe we should check carbon-14 dating just, to rule out. And then they find there's carbon-14 and it just opens up more cans of worms. And a lot of people were opposed to doing the test. Why? Well, we don't want to potentially open that can of worms, which has been opened. So you go to something with a longer half-life. Something like what we talked about in class, that is the uranium lead. You have uranium-235 and uranium-238. Uranium-235 has a half-life that's, I think, 700 million years. So that's going to date things that are relatively recent, like, I don't know, life. Right? If they believe that life, the Cambrian explosion was 541 million years ago, then that's a good scale for measuring the early days of life. The uranium-238 has a half-life of 4.5 billion years ago. Well, that's good for measuring back to the beginning of the Earth with our current understanding. They also have other ones like potassium, argon dating, and strontium rubidium that have different half-lives and different abilities. So there's different methods used to measure old rocks compared to living things. My last thing on radiometric dating is looking at the Shroud of Turin, just because, we talked about Utsi, and Utsi was totally interesting. The Shroud of Turin is also interesting. So the Shroud of Turin first turned up in the 14th century, as in the 1300s. Yeah, I think it says late there, doesn't it? Late 14th century. No, it just says 14th century. Okay, so in the 1300s, this Shroud of Turin was discovered. I don't know why. Where was it discovered? I don't think it's here, but it's in the name. Where was it discovered?
Turin.
Yeah, in Torino. Turin and Torino are the same place. And I don't know how people decided this must be the shroud of Christ, but they did. And so it's considered a sacred, holy thing. And of course, a lot of scientists are like, really? Like, how do you know that's the face of Christ? All you know is that's the face. You know that this is a death shroud. That's all you know. And so finally, after a whole lot of arguing and stuff, in 1988, they actually took a little sample from an area that was already damaged to do radiometric dating. And they found it to be 728 years old. Now, we all know our dating system. It's not perfect, but it was done in 100 AD with a dividing point of Christ's birth. So BC means before Christ was born. AD means in the year of our Lord, so it's starting in the year he was born. And there's no zero in between. There's little things like that. But 1988, if you go back 728 years, does that take you to roughly 33, the age we believe Christ was when he died? Not even close. That takes you to about 1260 AD, which would be maybe 100 years, plus or minus 50 from when it was found. So that would seem to say, yeah, this was something that was recent when they found it, and clearly not Christ. Problem solved? If you're a true believer, I'm a true believer in the Bible, right? A lot of people will find that very annoying. You can't argue with him. He's got an out for everything. He just won't accept facts. I say that about people who believe the earth is flat. I understand where they're coming from, so I'm willing to take it. The true believers in the Shroud of Turin said, well, you took it from a region that had been patched. They found it, they patched it, you measured the age of the patch. So what you need to do is, come and measure something here that's not been damaged, and I don't think that's ever been done. But the true believers are like, the dating is flawed because you just only know the date of the patch and not the date of the original cloth. Let's skip over that. I do want to mention tunneling. Just a fun topic. You're not going to be held responsible for tunneling in any way, shape, or form. Tunneling is what happens when you have, this situation is illustrating tunneling. Imagine that you have a cone with a caldera, and it's nice and smooth, and you have a marble that you're rolling in there. The marble has enough energy to get up to this point, right? At that point, all of its energy is potential, no kinetic. And then it rolls back down, rolls up here, and just rolls back and forth. That's a very classical problem. In quantum physics, we can make the same problem But in quantum physics, the location is not so simple. Because in quantum physics, what are you saying that particle is? We are going to have some quantization, not what I'm looking for. The whole de Broglie thing. That particle is also a wave. But when you define the location of the wave, it's a little different. Right? You have a wave like this, and I say, where is the photon? You say, well, it's somewhere in that region. It's proportional to the amplitude squared to calculate the probability of it. But it could be anywhere in that range, except for the places where it's crossing zero for the electric field. So we have the same thing here. The wave function is going to say that the particle could be anywhere here. Now, the probability is much, much higher in here than it is out here, but it's not zero out here. And so quantum physics says I can measure that particle and I find it here, and then I make a subsequent measurement and I can find it out here. Now, once it's out here, it's going to keep going, just like the marble would once it's outside. But quantum physics says it can pass through a barrier that doesn't have enough energy to get past because its location is delocalized. It's spread out and has certain probability of being outside. So we call that phenomenon tunneling. So we would say that this electron, if this is an electron, a marble, if it was my example, tunneled out. We use the term tunnel because it's like a prisoner trying to get out of prison. They can't go over the wall, so they tunnel underneath. That's actually the origin. Now, that's interesting. Is it useful?
Sure.
Sure. Yes, it's absolutely useful. It's absolutely useful because it's something that occurs with radioactive decay. If you take something like the alpha decay of a uranium atom, you can treat it, the alpha particle is like this little thing that is bouncing around inside, or quantum mechanically, it's a wave. And you have the potential energy function, like the well that we showed here, is shown with the red line. And it has an energy, let's say the energy is up here, it's not enough to get over. But quantum physics says there's a certain probability of it being outside. And so basically we talk about it like it's bouncing back and forth, and every time it gets to the edge, there is a probability that it will get past the edge, even without having enough energy. And when we have that radioactive decay, that's when the tunneling occurred. And so we can actually use that model to calculate what the half-life should be or what the decay constant should be. And we get at least the right ballpark, right order of magnitude calculations for half-lives of different nuclei based on this model. And of course, you're still probably, you said it'd be useful, and that doesn't seem all that useful, really. It helps to explain something, but how's it useful? Where here's a way that it is useful. This is just showing what the wave functions look like inside and outside. The scanning tunneling microscope. A scanning tunneling microscope is created by having a tip, and this tip you can't tell from the picture. That tip is atomically sharp. What does it mean to be atomically sharp? It's something like this. And so you take this tip and you bring it close to a surface. And when you bring it close to the surface, you're making this barrier smaller, right? Because you have the wave function for it being here and the wave function for it being here. You bring it closer, and the overlap of those makes it so it's a smaller barrier. And then you put a voltage. So like, let's say I put this plus and this minus. And what I'm talking about is the wave function for an electron. And so if I have that plus and minus, the electrons are naturally going to be pulled to the positive, right? And so I can have a certain current flow. Well, that's charge moving. That's electrons moving. The current is obviously going the opposite direction of the electrons. So I have a current. And based on the height of this barrier and the width of the barrier, I can calculate what the tunneling probability is, and thus I can calculate what the current should be based on the distance. And so as a result, we can actually measure how big that tunneling current is, and it tells us how close the tip is to the surface. So this tunneling phenomena allows us to calculate how close the tip is to the surface. And then with the scan tunneling microscope, you actually can run it in different modes. One mode is the constant current mode, and so you move the tip across and you raise and lower to keep the current constant. And then your height is matching the height of the sample. Or you can do it in a constant height mode where you just take it across like this, and the current changes as the distance between the tip and the surface is varying. And so using these, they can plot all kinds of interesting features. Now they're actually dealing with the wave functions for the electrons, and so you can actually see something about the atomic orbitals of the surface. Got a question, Leslie?
What exactly is that picture below?
Which part? The top part?
The bottom.
The bottom part? Oh, that's just an insect. I don't know.
I was like, it looks like
It says the head of a Coleoptera chrysomelida. Melidi, whatever. Now, in order for this to work, this has to be a conducting surface. So to see this head of the insect, you know the insect's head's not conducting, right? So what they have to do is they have to coat it with something conducting. You want to coat it with something that's not going to be a very thick film, so they typically coat them with gold. Coat it with a very small amount of gold, and then you can do the STM. Okay, let's review. So starting off, we started the semester with electricity and magnetism. And so we have a lot of things with electricity that we're long removed of that we have to remind ourselves about. Yes?
Is this going to be put on Moodle where we can see this?
Yeah.
Okay.
So electric charge, remember we have positive charge, negative charge. What's the fundamental unit for positive charge? Yeah, protons.
Okay.
Oh, okay.
And for negative charge?
Electric.
Electrons, excellent. And we have Coulomb's law to tell us about the force between them. So we have the force is K Q1 Q2 over the separation squared. And our rule that opposites attract, likes repel. It seems really simple now, doesn't it, compared to when you first learned it? Just been a long time, yes. So, simple rules, charge can't be created or destroyed, Coulomb's law. Then these are forces, they have direction. You find the magnitude of the force, find the direction, do the two separately, and then work problems as vector problems. We then shifted to talking about electric fields, where the electric field is equal to force over charge. Now, it is a vector. That was a vector too, but I didn't put the r hat. So the electric field vector is just the electric force divided by charge. So for a point charge, and this is only for a point charge, red will work. So that red is only for a point charge. The electric field is KQ over R squared. I didn't put a vector sign. Since I have vectors, I better put an R hat here. What is the rule for directions of the electric field? If I have a positive charge, what direction does it point?
Toward negative.
Okay, it points away from positive and toward negative. So if it's a positive charge, the electric field is going to be pointing out. If it's a negative charge, it's pointing in. What's the purpose of the electric field?
To allow us to visualize changes in strength and stuff, so we can make predictions about how charges are going to react a certain distance from a object with a charge.
That's the point. It makes it easier for us to calculate the forces. We can calculate the electric field due to all this stuff, and I say if I bring a charge here, what's going to happen? Well, the electric field times the charge gives me the force. So it makes life easier for us. You can add electric fields. They're vectors. You add them as vectors. Electric field means if the lines are close together, you have a stronger electric field. Farther apart, it's weaker. The direction, of course, of the force is going to be parallel to the lines. Electric field lines, they can't cross. Because if the electric field lines cross, that would mean your net force has two directions. It's not possible. So electric field lines can never cross. They always start at a positive charge, or they could start at infinity. They always end at a negative charge, or they could end at infinity. Gauss's law says that, and for everyone who's not in physics 252, what you need to know for Gauss's law is that the electric field coming out of a region is proportional to the charge enclosed. For people in the other class, well, you've got a lot more there. Conductors and insulators. The difference in a conductor and an insulator is not one can have charge and one can't, or you can add charge to one and not the other. You can add charge or take away charge from a conductor or an insulator. The difference is on a conductor, some of the electrons, what we call conduction electrons, can move with virtually no energy charge. So the electrons move virtually free of energy, hence virtually no resistance as we got to when we talked about circuits. Whereas an insulator, you have to give electrons energy to raise them to a higher energy level before they can move. And so you have to use energy to make electrons move in an insulator. So you can put electrons on the insulator, you can take them off the insulator, you can't make them move without a lot of energy. Using Gauss's law, we can show that the electric field inside of a conductor has to be zero. Using Gauss's law, using just logic. If I had a conductor and I put an electron in the middle, if the electric field is not zero, it's going to have a force to make it move. So to reach equilibrium, we have to make it so, since you have conduction of electrons everywhere, so that the electric field is zero everywhere inside, so the electrons aren't being pulled around to reach a new equilibrium. So the charge density, well, the electric field inside a conductor is zero, and then using Gauss's law, the charge density inside of a conductor is zero. That is, the net charge is zero in any region inside of a conductor, which means all the charge has to be on the surface. Once again, using our rules of electric fields on the surface, electric fields have to be normal to the surface. If they had a component that was parallel to the surface, then an electron on the surface, which on a conductor you have electrons on the surface, would have a force pulling it sideways, which would change the electric fields until you have fields to the surface. If I have some crazy shape like this, the electric field lines have to go directly out of the surface at every location, and the electric field inside is zero. And the net charge inside is zero. Voltage, also known as the electric potential. Leslie was pointing out that the textbook had some differences there. The voltage is a potential energy per charge. So the same idea as electric field, but we use potential energy per charge instead of force per charge. And so for a point charge, so defined as, well, change in electric potential is defined as change in potential energy over charge. And so, yeah. So for a point charge, so putting in red for a point charge, actually, I'm going to write the whole thing here. For a point charge, the voltage is KQ over R, the electric potential. Where voltage is zero when you're infinitely far away, the electric potential is zero when you're infinitely far away, and approaches infinity when you're right at it. Now, if I have a positive charge, is it attracted or repelled from other positive charges? Repelled. So if I have a positive charge, it's going to go away from a positive charge. The electric potential from a positive charge is positive and drops as you go away. So that means that a positive charge is always going to go toward lower electric potential. Negative charge does the opposite. A negative charge will always go toward higher electric potential. In both cases, in terms of energy, what are they doing? Going toward lower potential energy. In all cases, they're going toward lower potential energy. Naturally. Obviously, you can force them against their will. Capacitors. A capacitor stores energy in the form of either an electric field or a charge separation. For our work, the net charge on a capacitor was zero. You put a positive charge on one side and a negative charge on the other, the total charge is zero. It's not storing charge, but it's storing a separation of that charge. And so you have energy because the charge, if they're opposite charges, they want to come together. And so that's where you have your potential energy. We talk about the capacitance that is defined as capacitance is defined as Q over V. It's the charge separation Q divided by the voltage difference across the capacitor V.
Just to be sure about this, when you say the charge separation, is that when you take like the something minus another thing or whatever? The two charges?
Okay, so I'll start with just a parallel plate capacitor that has Q initially equals 0. No charge on either plate. And then I'm going to connect that to a battery. You know it's a battery because it has two cells shown. And which side's positive on that battery? The longer side, the left side. And so what's going to happen now is the positive side is going to pull electrons off, making this become positive. The negative side is going to push electrons away, making this negative. So when we connect that, we're going to have a positive side and a negative side. And so then we'll have plus Q on this side and minus Q on that side. And if I measure the voltage difference, sorry, my writing wouldn't fit. Delta V is the difference between those two. Then my relationship is C is equal to, I'll just put the plus Q over that delta V. That's the definition of capacitance. And for parallel plate capacitors, the only kind we learned about, that's equal to kappa, which is telling us about the dielectric constant, epsilon 0, the plate area divided by the separation of the plates. So you have two plates of area A and that are separated by distance D. So those are the physical parameters. So we can calculate a physical capacitance based on how it's constructed. And of course, real capacitors, they usually aren't parallel plates. They're something like, let's take two sheets of conductor, let's put an insulator between them, put an insulator on the outside and roll it up tight. Roll it up tight so D gets smaller. If D gets smaller, what happens to the capacitance? It increases. And you have these sheets, so the area is large. What does a large area do? Increases it. Finally, that insulator, the bigger the kappa, the bigger the capacitance as well. Another thing that's important with capacitors is the breakdown voltage. If you do anything with circuits, you want to make sure that your capacitor can withstand the voltage. You're going to put 600 volts on it, you need to make sure the breakdown voltage is bigger than 600 volts. The breakdown voltage is the voltage that's going to be high enough to make an arc occur between the plates. So if you have air, we learned, I think this goes back to Andrew's group from the first lab, that the breakdown voltage is, what was it, 300,000 volts per centimeter? I think that's what it was. But in air, it's a pretty big breakdown voltage. If you go to other insulators, it's usually bigger. Obviously, put a conductor, it'd be smaller, but that would be dumb. And so that's how you get that breakdown voltage, and it's important to check. Because once you break down, you'll damage that insulator, and then everything's off. All right. Electric current, resistance, and Ohm's law in 1 minute. Current is the rate at which charge is flowing through a circuit. In physics, we talk about conventional current, which is charge passing per unit time. We measure charge in coulombs, so it's positive charge per unit time, which causes a bit of a difficulty because in a wire, it's always electrons that are passing. And so the electrons are passing in the opposite direction of the, quote, positive, end quote, charge. The result being that the electrons flow the opposite direction of the current. And now I am out of time, so Friday, starting with Ohm's law.
What is the best way to study for this test since it is so much information?
It is a lot of information. The best way, I think, would be to look over those worksheets from each chapter. I think that's going to be your best way.
Okay.
And I have more worksheets coming at you.
Oh, wait, you're gonna do some for these last few ones?
I think I have to.
Okay, okay. So quick problem, I guess.
What's that?
I don't know why, because the grade calculator is supposed to show us the minimum to get from the applying